Hello, I am Dylan Campbell. Welcome to the third talk of the tutorial on deep declarative networks at ECCV2020. This one consists of some hands-on coding using the DDN codebase, which can be found at deepdeclarativenetworks.com. Let's go there now. The codebase is broken into several sections. We will be spending most of our time in the tutorials directory, but before we go there, let's have a quick glance at the library itself. The library is broken up into a basic and a PyTorch branch. The former is written in Python with NumPy and SciPy and is primarily for teaching and learning purposes, while the latter uses the PyTorch framework, which we'll be using in this tutorial. The main code is in node.py, where we define the allowed optimization problems, including unconstrained, equality constrained, and inequality constrained problems, and efficiently implement the backward pass for each with batchwise computations that are efficient. While we won't be looking at this code in detail during this tutorial, this is where you can go if you want to see how we have implemented DDNs in PyTorch. Now let's head over to the JuPyter Notebook tutorial. I'm going to go through 3 examples of declarative nodes in this tutorial, showing their behavior and solving some simple bi-level optimization problems. We're not going to look at training any full networks in this tutorial, but the PyTorch layers that we create can easily be used inside a network. So the first one is minimizing the KL divergence over the probability simplex. We're going to be considering the problem of minimizing this divergence between the input x and the output y, subject to the output forming a valid probability vector. That is, the elements of y have to be positive and sum to 1. We can write this formally as follows, using the argmin notation. And we have a constraint here that the sum is equal to 1. The positivity constraint on y is automatically satisfied by the domain of the log function. A nice feature of this problem is that we can solve it in closed form as x divided by the sum of x. However, we're only going to use this for verification and pretend for now that we don't have a closed form solution. Instead, we're going to make use of the SciPy optimize module to solve the problem via an iterative method. We derive our deep declarative node from the linear equality constrained node class. And for this class, we need to implement 3 functions: the objective function, the solve function, and the linear constraint parameters function. The gradient function is already implemented for us in the DDN node code that I showed you earlier. Okay, so this is what it looks like. We're going to define a class min_KL, and we're using this linear equality constrained declarative node here. So as I said, we need to define an objective function, so we just convert the equation into Python and PyTorch code. And we've got the x log y, taking the sum of that and negating it. Then we have to define the linear constraint parameters, which define the condition that the sum of y equals 1. So here we define A to be the transpose vector of 1s and D to just be a single scalar 1. The heart of the implementation is the solve function. So this is the forward pass of the network, and here we are going to solve the constrained optimization problem using SciPy's built-in minimize function. And we're going to initialize the solver at the uniform distribution, which we do here. We do have to loop over the batch for this because we're using SciPy instead of a built-in torch function. But we call the minimize function with the objective function defined here, the KL divergence. We have the constraint that the sum of u has to equal 1, and we have some bounds here to keep it feasible. We would usually return 2 arguments. In fact, we have to return 2 arguments, both the solution and the context. The context is just some cached values that make it simpler to compute the gradient. But in this case, we don't need to do any, so we just return none. And now we test the node. So we generate random values of input, so 5 random values, and we expect it to be the x divided by the sum of x. So let's see what we get. As we can see, the actual output is identical, almost identical to the expected output. We're now going to plot the function and gradient, sweeping the first component of the input, x1, from 0.1 to 10, while holding the other elements of x constant. So we do this by, in a loop, changing x1, calling the forward pass function, node.solve, and also computing the gradient. The gradient is the vector Jacobian product. We also compute the derivative itself. This is an inefficient function call, and we only use it for teaching and analysis purposes. In PyTorch and many other frameworks, you only ever compute vector Jacobian products because they are much more efficient to compute. And then we plot out the results. So we plot the output y as x1 is varying. We plot the derivative dy dx1 as x1 is varying. And we plot the vector Jacobian product, where the vector in this case is just the ones vector, but could also be, for example, in a network, it would typically be your error signal from your loss function. And here we have the results. So we can see that the first component, as x gets larger, the output of this component gets larger as well, while the other components get attenuated. But they still all sum to 1 because they're valid probabilities. Our derivative, we expect mathematically that the first component will be replaced by 1 minus the first component scaled by some factor, and that the other components will just be negated and scaled by some factor. And this is indeed what we observe. And finally, the vector Jacobian product, we mathematically expect it to be exactly 0 for all components. And we can see that the scale here is 10 to the minus 7, so it has almost been achieved in this situation. Now let's see whether we can use the node within a bi-level optimization problem. We'll attempt to learn an input x that results in an output y with the smallest norm squared possible. We're also going to regularize the norm of x to be close to 10. Given our understanding of the KL divergence, this should learn a vector x that is a constant multiple of the ones vector, that is, all elements of x should be the same. So let's see what happens. So first we have to define the upper level objective, which we have said is the norm squared of y plus the norm of x minus 10, because we want to drive x towards 10, or the norm of x towards 10. We instantiate the node here, and then create a declarative layer, which is an instance of a PyTorch layer, and can be used in a PyTorch network in the standard way, in the same way, for example, as a convolution layer. Now we're going to solve this using gradient descent. So we compute the output by passing the input to the layer. We compute the upper level objective function, so the loss, and then we use z.backward to compute the gradient. We take a step in the negative gradient direction by adjusting the x values and save our loss that we obtain. We're going to do the same again, except using the LBFGS built-in optimizer in PyTorch, which should be a more efficient optimizer for this problem. And the results we get, indeed the x is close to 10, so it has a norm of 10, and they look fairly similar, although there is some difference between them. We expect them to be uniform, but that has not been entirely learnt yet. And this is the upper level objective if we plot it. So I'm going to zoom in because we can't see all that much. So I'm going to zoom in on these 500 iterations, and you can see that the loss function is steadily decreasing as we increase the iteration number. On the other hand, the LBFGS result also produces a vector x with a norm of 10, but it is clear that the numbers are much closer together. So this is more what we expect from this optimization problem. And you can see from the loss plot that it indeed drops down to a small loss within, say, 15 iterations. Okay, we're now going to move on to the second example, which is minimizing a robust pseudo-Huber distance, which can be thought of as taking global average pooling and replacing the average function with a robust average, in this case, a pseudo-Huber average. So we're trying to minimize the distance between the input x and the output y using this penalty function, which we write like so. Because this is an unconstrained optimization problem, we use the abstract declarative node class, and this means we only need to implement two functions, the objective function and the solve function. However, we're also going to provide a gradient function here to override the generic gradient computed by the DDN code so that we can compare the two to make sure that we are getting the correct gradient. And we are going to use an efficient hand-coded analytical gradient that uses the structure of the problem in its computation. Okay, so here we go. We call the class global pseudo-Huber pool 2D, and we write the objective function as such. And again, the solve function is the important one here. So this is the forward pass. We first detach the input. This means we don't want to track the gradient of the input, because in a declarative node, we do not keep track of the gradients of the tensors because we have decoupled the gradient computation from the forward pass. We initialize y to the average, and then we run optimization. And our optimization is again using LBFGS. So this is trying to optimize that objective function in the forward pass. And our gradient is here. We are overriding the base class to compute the analytic gradient, which makes use of the structure of the problem, which is always an option with DDN layers. Okay, so now we're going to test the node. We have a batch size of 3 and an input size of 6 by 6. So we have a 6 by 6 window that we want to compute the robust average over. And for the first batch element, these are the inputs we have. We have 6 by 6 of them, and we get an output, a robust average of about 0.2. We're now going to plot the function and the gradient as we sweep the first component of the input x1, so this component, from -10 to 10, while holding the other elements of x constant. So given the scale of these inputs, we can see that a value of -10 or +10 is going to be a considerable outlier. So if we were doing average pooling, we would get a very skewed result. But we hope, because we're doing robust pooling, that the result is not strongly skewed by this outlier. So to plot this, we just loop over, changing that value of x1 and calling the forward pass, so the node.solve function. We also compute the vector Jacobian product using the generic solver from the DDN code, which uses super to access this, and also our analytic hand-coded gradient. And then we do the plots. Okay, so our output is here, and we can see that the output y, as we're sweeping x1 from -10 to 10, the effect of this outlier is attenuated. So a value of x1 at 10 and a value of x1 at 2.5 make little difference to the robust estimate, which is what we would expect. And next we see the two vector Jacobian products that we've computed, and we see that the analytic one looks identical to the generic one, which is shows that the generic computation is doing the same thing as our hand-coded, mathematically derived gradient. Okay, we're going to move on to our final example, which is minimizing a perspective endpoint objective function, which can be used for camera localization to solve for the rotation and translation of a camera. So here we're going to minimize the weighted reprojection error between a set of corresponding 2D and 3D points. So 3D points are P, 2D points are Q, by varying the rigid transformation parameters Y applied to the 3D points. Here, the transformation parameters consist of an angle axis rotation vector concatenated with a translation vector. So we write the program as this optimization problem. We've got the sum, the weighted sum of the squared error, where the projection function pi uses the intrinsic camera parameters, the rotation and the translation, and maps these homogeneous coordinates to Cartesian using the usual approach. So because this is an unconstrained problem, we again use the abstract declarative node class, and we have to implement two functions, the objective function and the solve function. And for this class, we're going to use a function from OpenCV, which is solve PNP ransack. So this is showing you how you can use ransack inside your network, despite that being a non-differentiable algorithm. Okay, so as usual, we write the class in this way. We write in the objective function, which projects the points by the camera parameters y. We compute the squared error and take the weighted sum. Here we are enforcing that the weights are non-negative, but usually this would be done earlier in your network. As usual, the solve function is the heart of the implementation, which runs the forward pass. So here we initialize the transformation and then run the optimization. To initialize the transformation, we compute the ransack P3P solution, which is just using OpenCV, and the boilerplate code for the algorithm is here. So this is finding a robust solution to the problem to give us an initialization. And from this initialization, we run optimization, again using LBFGS. Let's run that. So we're now going to test the node with 15 random 2D, 3D point pairs, random camera parameters, and significant additive Gaussian noise. We're also going to add a single outlier correspondence. We should expect poor results for the PNP algorithm when there are outliers, but perhaps we can learn to identify such outliers in our code. Okay, so here is the boilerplate code where we generate the camera parameters, we generate image points and 3D points, and then run the solver using the solve function as usual. We get our output, where we can see that the camera parameters are significantly different between the true output and the estimated output. And this is particularly true because we can see that the rotation error is around 18 degrees, which is considerable. So it's clear that a single outlier can play havoc with standard PNP estimation. We can visualize this by plotting the 2D points and projected 3D points using the true and estimated transformation parameters. We're going to link the 2D and 3D putative correspondences with a line to make the outlier correspondence clear. As we can see, this is the outlier one here, and it is clearly an incorrect correspondence. You can also see from this figure the scale of the noise, because the points that are true correspondences are still fairly far apart from each other. So here the black squares are the 2D points, the red circles are the true 3D projected points, and the black circles are the 3D points projected with the estimated projection. So we're now going to try to learn the weights that will attenuate the effect of outlier correspondences. Our upper level objective function is going to be a weighted sum of rotation and translation errors because we know the true camera pose. We're going to expect that the outlier correspondences will be down weighted and perhaps some of the noisier points as well. So we define the upper level objective function here. We compute the rotation error in radians and the translation error. We sum them up and have a factor, a hyperparameter that scales between them. As usual, we form a declarative layer, which can be used in any PyTorch network, and compute the optimum using the LBFGS optimizer. Okay, and then we print out some results. So our weights that we have found are here, and we can see that there are a bunch of zeros here. So it's identified a bunch of the components of our input as outliers, and it has driven the rotation error down to 0.03 degrees, and the translation error down to 0.08. So this is a good sign. Let's plot the learning curves. So we have the loss function, which we can see is steadily decreasing, and the rotation error is also decreasing from 18 degrees down to 0.03 degrees. There is a similar story for the translation error. We can visualize the results by plotting the 2D points and the projected 3D points. And we're going to scale the points by the estimated weight and replace ones with a weight of 0 with crosses. So you can see that the outlier is clearly identified as such, and points with a larger amount of noise are down-weighted or identified as outliers. Okay, that's it for the hands-on coding part of the tutorial. Please feel free to explore this notebook at your leisure, as well as the other tutorials in the codebase. Thank you very much for your attention.
I would like to thank Dylan for this hands-on coding session. At this point in the tutorial, you should be able to start coding your first DDN layer and integrate it into your network. In this session, you learn how to use the DDN codebase for minimizing the KL divergence over the probability simplex and how to use that node in a bi-level optimization problem. You also learned how to minimize a robust pseudo-huber distance and a PNP objective function. In the next session, Steve and Diamond will introduce their approach to differentiable convex optimization layers. He will discuss convex optimization, domain-specific language for optimization, parameterized convex problems, and how these concepts are all brought together in the CVX Pi layers package.